we are going to find the power series solution centered at 0 for this differential equation here. So let's get to work. We know for y prime, we are going to change this to the power series when n goes from 1 to infinity. Remember, for the first derivative, n starts at 1. And then inside, we will have n times an x to the n minus 1 power. That's the first derivative, right? And then we will add this with 2x times y. Y is the power series when n goes from 0 to infinity, an x to the n, and this is all equal to 0, just like this. If you differentiate this one time, you get that, and you lose the constant term. That's why n starts as 1. Anyway, this is what to do next. As we can see, here we have 2x. We can, of course, multiply this with that. So let's get to work for this. We will be adding this with the sum when n goes from 0 to infinity to an. And then x to the first power times x to the nth power is x to the n plus 1 power. And this is equal to 0. And we should also write this down, right? So let me just put that down right here as well. N goes from 1 to infinity, an x to the n minus 1. Okay. This is what we're going to do next. As you can see, the exponent of x are different. This right here is x to the n minus 1 power. This right here is x to the n plus 1 power. Our first goal is to make sure that the exponents of x are the same, right? So since this is n minus 1, since this is n plus 1, why don't we make them both equal to n? How's that? So let's focus on this. My goal right here is to make this into x to the nth power. How can I do that though? Well, in order for me to make this into x to the nth power, as we can see, originally we had n minus 1, and now this is n. What I did is I just add 1 to the n, isn't it? For this right here, inside, for this formula right here, whenever we see the n, we are going to add 1 to it. So right here, this is going to be a n plus 1, all right? And then this n is going to be n plus 1 as well. I'll put this in the parentheses. And then from here to here, yes, I just totally changed the whole thing. But this is what we can do to compromise it. We add 1 to all the n's right here. All we have to do now is to subtract 1 here, subtract 1 from here, and that will be it. So this is going to be n goes from 0 now to n minus infinity minus 1, still infinity, just like that, right? Okay, so that's what we have. And now let's see what we have from here. We can say this is adding. Well, here, I am going to be subtracting 1 in order for me to reach x to the nth power, isn't it? So right here, you see I minus 1. So this n, I will have n minus 1, right? So let's put that down right here as well. This is a sub n minus 1. And then here I have that 2. And because I subtract 1 from here and here, to compromise it for the sigma notation here, I have to add 1, isn't it? So this is going to be the sum when n goes from 1 to infinity now. And maybe I should make this starting value stand out as well. This is 1, and this is equal to 0, just like that, right? When you subtract 1, you have to add 1, add 1. Infinity plus 1 is still infinity. When you add 1 right here, you have to subtract 1, subtract 1. All right, so that's the first fixed. And now, the second fix is that we have to make sure that the starting index are the same. This is n is equal to 0. This is n is equal to 1. You are always going to take care of the smaller starting index right here, right? To fix this, this is what we do. Remember, this notation tells you to plug in n is equal to 0 into this expression. That will be the first term. And plugging n is equal to 1 into here, and that will be the second term. And you add them up, right? So first, I will just plug in let n equals to 0 into here, 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 and let's see what we get. So let me write it down for you guys. 0 plus 1, and then times a 0 plus 1 for the index right here, and this is times x to the 0th power. This is what we get when n is equal to 0, right? Let me just kind of indicate that for you guys. And anything after that is n is equal to 1, n is equal to 2, so on, so on, so on. And we can put them together as the sum when n goes from 1 to infinity of everything like this, right? So I'll just write this down. n plus 1, a sub n plus 1, and then this is x to the nth power. So this right here, it was just for that, okay? And now we can just write this down here, plus the sum when n goes from 1 to infinity, 2 a sub n minus 1, x to the nth power, and everything is still equal to 0. Okay, so what is this? This is just 0 plus 1 is just 1 times this is a1, right? So this is just a1, isn't it? And yeah, so let me just write it down like this. This right here is just a1. And now this and that, because the sigma notation, they have the exact starting n value and also the n value, we can put them together. So let's do that. This is the series when n goes from 1 to infinity. And inside, you see, both of them have x to the nth power, so we can factor that out. Let's put that at the end though. So let me open a big parentheses right here, and then for the x to the n, we'll just put it at the end, and this is equal to 0. And for this right here, let's just put that down first. N plus 1 times a sub n plus 1, and then we add this with 2 a n minus 1, just like that. Okay, so this is pretty much the things that we can do, right? And now you see on the right hand side, it's all equal to 0. That means a1 has to be equal to 0. It has to be. Because on the left hand side, this is the constant term. Everything in this series, when n is equal to 1, you have x. When n is equal to 2, you have x squared, and so on, so on, so on. Well, this is the polynomial with variables, and the constant term has to be 0 in order to make the right hand side 0. And also, for the coefficients of each term, they all have to be 0 as well, right? Well, with this being said, we can say n plus 1 times an plus 1 plus 2 an minus 1 has to be 0. From here, we are going to solve for a with a bigger index, which is this. So let me do this. An plus 1. We have to move this to the other side, so it becomes negative 2a sub n minus 1. And then we have to divide by that, right? So divide this by n plus 1, just like that. And now this is going to help us out to find the coefficients in our power series solution. Remember, our y is in the form of the series where n goes from 0 to infinity, an x to the n. If we can figure out what an's are, we are done, right? And this is going to help us out. This is the recursive formula though. And in order for us to figure out a pattern, the best thing for us to do is draw a table and then list out a few values for it, and then we can see if we can have a pattern or not. So we are going to do that. First of all, we know a1 is equal to 0. That's good. But in this right here, n began with 0, right? When n is equal to 0, we must have the a0 term. But what's a0? Well, we don't know, right? So this is how we're going to do it. We know a0. We'll just assign this to be arbitrary, all right? Meaning that this is just going to be a random constant for the moment, all right? It can be anything. And you know this is going to be the c, the constant c that we used to have, right? So let me just write it down like this. And that's also line up. Since a0 is arbitrary, and we can write down the next one, which is a1, and we know this is equal to 0. That's great. Okay, what's a2 then? I don't know yet. To get a2, I have to utilize this. And let me just put this down right here for you guys, right? So I'm going to choose some n values, and this is going to help us out with a2, a3, a4, and so on, so on, so on. And let me just put down the formula right here. Anything a, whatever, you know, this is an plus 1, which you know this is equal to that formula, negative 2an minus 1 over n plus 1. This formula is good for n is 1, 2, 3, 4, 5, and so on. Because when n is equal to 1, we can get a2, right? So this is how we are going to do it. Let me just draw a few of this, right? And this is how I would suggest you guys to do this kind of table. First of all, you know n start with 1 for this table, right? And of course, just keep going. 2, 3, 4, 5, 6, 7, so on, right? Depending on how many that we need to have. And plugging 1 into here, you'll get A2. And then plugging 2 into here, you get A3. The tip to do this kind of table is that focus on one item and then just do them vertically. Just like how you use Excel, right? Just click on the little corner and drag it down below. So you know the pattern. This right here is going to be A4, A5, A6, A7, right? And then equal sign, equal sign, equal sign, equal sign, equal sign, equal sign. -2, right? It's just a constant multiple, so everybody will have that -2. So let me just put down the -2, right? All right, now, when n is equal to 1, this term is going to be a of 1 minus 1, which is a0. And then you know this right here, when n is 2, you get 2 minus 1, which is 1. So this is a1. And then you know this is going to be a2, a3, a4, a5, and so on, right? And then on the denominator here, 1 plus 1, which is 2, 2 plus 1 is 3, and so on. You know this is going to be 4, 5, 6, 7. This is the fastest way to fill in this kind of table. Just focus on one item and then just do it vertically, all right? Okay, so let's see if we can simplify anything. This right here, 2 and 2 cancel out. Of course, we will just have negative a0. And a0 is arbitrary, so you will just keep it as how it is. This one is excellent because we know a1 is equal to 0, so this is just going to be 0, right? So we don't need to worry about this. Next one, we can reduce this. This is going to be -1/2. A2 is what? A2 is this, which is negative a0. So let's put this down right here, negative a0, and we'll multiply that. So altogether, this is going to be positive a0 over 2, isn't it? And this one is also going to be good because a3 is equal to 0, so everything's going to be 0. And the next one is going to be a4. A4 is going to be this, and let's reduce the fraction first. This is negative 1/3. A4 is that, which is a0 over 2. And let me just leave it as how it is, all right? And a5 is 0, so this is 0. And I think I should do one more for you guys. So when n is equal to 7, 2, 3, 4, 5, 6, 7, 8, a8, and then equal sign, and then the -2, and then this right here will be a6, and then 8 on the bottom. This right here, reduce that, you get -1 over 4, a6, which is this right here, and just put this down, all right, just as how it is. We will be multiplying this with -1 over 3 times a0 over 2, like this, right? And I think we can see the pattern already. You see that we have -1 a0, 1 over 2, and this is -1 over 3 times 2, and this is going to be positive, right? And this is 4, 3, 2, and if you would like, you can have the 1 at the end, right? Here's a little hint. Whenever you have like dividing by n or multiply by n, you are going to get some kind of factorial. Even though this is n plus 1, we'll still end up with some kind of factorial, all right? Anyway, all the odd number terms, you're not looking at these n's. You're looking for a1, a3, a5, a7, right? All these are 0. We know our solution is going to be in that form. So we have y of x is equal to the first term, it's the constant term, namely a0. So let's put this down right here. And the next one is going to be plus a1 x to the first power. And the next one is going to be a2 x squared. And the next one is going to be a3 x to the third power. And let me just write down a few more for you guys. a4 x to the fourth power plus a5 x to the fifth power plus a6 x to the sixth power plus a7 x to the seventh power. And then we also have a8. So we will also write that down. a8 x to the 8th power, and of course keeps on going forever, right? And now you know a1, a3, a5, a7, they are just zeros, right? So these terms don't matter anymore, right? And now if you would like, you can also look at this. For a0, a2, a4, a6, and a8, we're just going to put in all these values accordingly. First of all, we have the a0, so let me just write it down. And the next term we will have plus a2, which is this right here. let me write it down as negative a0, that's a2. And then we multiply this with x squared, right? And a4 is going to be right here, which is 1/2 a0. So let me put down plus 1/2 a0. So I will put down 1/2 like this on the side, and then a0, and then x to the 4th power. And then next, a6, which is this right here, right? Let me put this down as parentheses negative 1/3 times positive 1/2. And we have the a0 on the side like this, and then I'm leaving a little space. And this is multiplied with x to the 6th power. And last term, a8, which is this. And you know, negative times negative becomes positive. So we will just have 1/4, 1/3, 1/2, right? So let's put that down. 1/4, 1/3, 1/2, a space, and then a0, and then x to the 8th power, and so on forever. And now this is what we have. And as you can see, right here, if you want to put this down as times 1/1 times 1/1, we can complete the factorials in the denominator, isn't it? Likewise, I can do it right here as well, times 1/1, and this one doesn't really matter that much. Anyway, everybody has a0, so we can factor that out all the way in the front, right? And then let's put this down like this. Here I have the 1, right? And then here I have minus 1, and then this is x squared. And then this term right here is pretty much plus 1/2 factorial, and then a0 is out already. And then we have the x to the 4th power. And then this is going to be minus 1/3 factorial, isn't it? And this is x to the 6th power. And then this is going to be plus 1/4 factorial, and then x to the 8th power, like this, and then keeps on going forever. The next one should be minus, so let me put on minus like this, right? And it keeps on going forever. Okay, depending on the direction of the question, if you want the first 3 non-zero terms or whatsoever, then just write down this, that, and you're done. But usually, you want to try to come with the pattern so you can put this into the closed form with the sigma notation, and we'll do that right here. This is a0. All right, let's look at what can we put on for this. So we are going to have the sum, and n goes from 0 to infinity, and you'll see why. Technically, this is when n is equal to 0, n is equal to 1. And notice that this n are not the same as those n, because I'm looking at this right here to write a formula for my final answer, all right? And this right here is n is equal to 2, n is equal to 3, n is equal to 4, and so on, right? Once again, this n's that I'm using right here, it's not the same as those n's over there. Anyway, we have positive, negative, positive, negative, positive, negative. So on the top, I should have a negative 1 raised to the nth power, because I want to have positive term first. This is good enough because n starts with 0, right? So the first term is positive, next term will be negative, next term will be positive. All right, divided by, this is the same as saying if you would like to put this down as divided by 0 factorial, because by definition, that's equal to 1. If you would like, you can write this down as divided by 1 factorial, right? And this is 2 factorial, this is n is equal to 3, this is 3 factorial, and so on. So you know, divided by n factorial. Excellent, right? Okay, x is just x. But when n is 1, the exponent right here is 2. When n is 2, the exponent is 4. So we have to do 2n power, isn't it? So right here, we will just write this down, perhaps in red. This is 2n power. This right here is it. This is our power series solution, right? This is our power series solution. Okay, do you want to know how to solve that in like 1 minute or so? I'll show you. So here is the old way, right? Okay, so let me just write it down and guess you can count. And if you would like, you can put down dy dx, right? I haven't finished copy down question. Do not start the clock yet, right? And here we go. This is separable, so let me move this to the other side. So we have dy dx equals to, this is the same as negative 2xy. Divide both sides by y, so we will have y right here, and then multiply both sides by dx, so you have negative 2x dx, and then integrate, and then right here you get ln absolute value of y. Don't put on plus c, this is equal to, on the left hand side you have negative x squared plus c, right? c1 if you like. And then you do this, you do that, and then you know this and that will cancel, and then you have absolute value of y is equal to, this is going to be c2 e to the negative x squared, isn't it? And then you can get rid of this, get rid of that, plus minus, right? And then at the end, y is equal to a legitimate c. This is all you need to do, which is e to the negative x squared, right? I don't know if that's 1 minute or not. This is a solution to that. And check this out. We know, let me write it down. We know e to the something, e to the x, this right here, is the sum when n goes from 0 to infinity, x to the nth power over n factorial, isn't it? Well, here we have e to the negative x squared. All I have to do is plug in negative x squared into here. Then you get the sum when n goes from 0 to infinity. And inside here, we will have negative x squared raised to the nth power over n factorial. This is the same as that. Anyway, it's either it's cool or maybe it's depressing. Up to you. Leave a comment down below. Let me know.